In this lesson, we're going to get familiar with logarithmic equations and formulas. So in math, we have always this backwards thinking, adding, there's subtraction, multiplying, there's dividing. We talked about square and square root. The inverse or backwards thinking to exponent is what's called a logarithm. So a logarithm kind of, again, works this backwards thinking. So whatever the exponential function does, the logarithm undoes. So for instance, if I do two, let's think about thing to work here. If I do 2 to the third power, we know that's going to be 8. If I go backwards, I can take the log of 8 base 2, and that's going to get me back to the 3. So on your calculator, we have 2 to the third power would be like 2 to the power of 3. That gives me 8. To do a logarithm of a base 2, we actually can go like math. If we go down here to number, I think it's like A. Yeah, log base. If I hit that one, hit enter. If I put a base of 2 in and put an 8 in there, hit enter, and also that gets back to the 3. So it kind of does reverse thinking. So if I have, 5 to the power of 2 is equal to 25, if I go backwards, I can say the log of 25 base 5 is going to get me back to the 2. So that's what a log does, is it does the backwards part of it all. So notice if I do 5 squared on the calculator, it gives me 25. But if I do math and hit alpha A, put a base of 5 there and a 25 in, if you hit enter, that gives me 2. So notice that the answer to a logarithm is actually the exponent of the base that gives you the 25. So keep that in mind. That's how logarithms kind of work. So like, if I want to do the square root of, say, 36, a lot of times we have to ask ourselves, well, what can you square to get 36? And if you can see that as 6, that square 36 is 6. If I want to know, say, the log of 36 base 6, what I'm asking myself is 6 to the what power gives me this 36? And that would be a 2. So the log of 36 base 6 would be 2. So that's kind of where logarithms do, is they kind of undo what an exponent does. So that's kind of where we're going to be going. So as I touched on some things, there's what's called an exponential equation, and then there's what's called an equivalent logarithmic equation. So a logarithmic expression is going to be an expression that contains at least one term with a logarithm, and there's 3 basic components. There's the power. So there's 3 basic components of a power: the base, the exponent, and the result of the exponentiation or power, if you will. So those are the 3 things here. So if I look at 3 to the 4th, notice that the 3 is the base, the 4 is the exponent, and 3 to the 4th would be 81. That's the result of the exponentiation or power. So this is what we call an exponential form. If I want to go logarithmic form of this, we have a log. If I do 81 base 3, that's going to equal 4. So this would read as 3 to the 4th power equals 81 in logarithmic language. These are equivalent. So those are interchangeable. So what you want to do is, what we want to pick up on is, how do we write an exponential form into a logarithmic form that means the same thing? So pay attention to where things go. So if I have x equals b to the y, notice that the base becomes the little subscript number of the log. The x becomes the result of the exponentiation. This becomes what we're taking the log of. And then the exponent actually goes to the other side of the equation. So what we pick up on is that. So notice how they're saying x is the result, and it also becomes the beginning or the argument of the logarithm. So we're going to pick up on those things here. For me, what I pick up on is the base is the little number, and the exponent goes to the other side of the equation, and then the x just goes in the remaining spot, which becomes what they call the argument, or what we're taking the log of. So if I want to write this equation in an equivalent logarithmic form, I like to go ahead and just write down the log to start with, and the equal sign, because we're going to make a logarithmic equation. Notice how the base is 2, that's going to be my little number. The 4 is the exponent, it goes to the other side. And then the 16 becomes what we take the log of, the argument. So the log of 16 base 2 is equal to 4, is what we call the logarithmic form. So if I have 3 squared equals 9, I can write this as log equals, and then I place the 3 becomes the base of the log. The 2 becomes the other side of the equation, that's where the exponent goes. And then the 9 becomes what we take the log of. So the log of 9 base 3 is equal to 2. It means the same thing as 3 squared equals 9. Those are interchangeable. So if I have 2 to the negative 2 equals 1/4, I can write this as the log of equals. So the base is going to be 2. The negative 2, the exponent goes to the other side. Then the 1/4 drops in as my argument while I'm taking the log of. So the log of 1/4 base 2 is equal to negative 2. So that's how we read that. I read this as the log of 16 base 2 is equal to 4. That's how it's read. So how I write it and how I read it are not quite the same thing. So if we want to write this logarithmic form into exponential form, notice that the base is 2, the exponent is the 5, and then that's going to equal then the 32 becomes the result. So 2 to the 5th power does equal 32. That's what's called exponential form. So if I have the log of 81 base 3 is equal to 4, the base is the 3, the 4 is the exponent, and 3 to the 4th, the result would be 81. That's the exponential form. So if I have log of 1/25 base 2 is equal to negative 2, again, the 5 is my base, the negative 2 is my exponent, and the result is going to be the 1/25. So if I have the log of 1,000th base 10 equals negative 3, I can write this as 10 to the negative 3 is equal to 1,000th. So that's what we call exponential form. So that's what you want to get kind of familiar with here, is recognizing that a logarithmic equation is a fancy way of writing an exponential equation. And it's got some uses as if we move further into all this. I don't think we're going to get too far into it. I think, again, we're just going to get exposed to some of the math here. So using a calculator, we want to be able to evaluate the log of 10,000. The log of 10,000, this is what's called a common logarithm. This space is understood to be a 10. They just won't write it there. So the log of 10,000 is really the log of 10,000 base 10. So what that is saying is, the log of 10,000 base 10 is equal to what? So in other words, 10 to the what power would give me 10,000. So if we could answer that question, we won't need a calculator, but if we want to use a calculator, there is an LOG button on the calculator. Just hit LOG and type in the 10,000. That's 4 zeros, yeah. And that should give me 4, because 10 to the 4th power would be 10,000. So that answer would be 4. So if I want to figure out the log of, that's going to be like tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionth. So that's the log of 1/1,000,000th. So if I want to evaluate the log of 1/1,000,000th, I can just use a calculator. The log of, that's like what, 5 zeros? 1, 2, 3, 4, 5. Yeah. So 1, 2, 3, 4, 5, 1. And that gives us then a -6. So that would be the exponent of the base. 10 to the -6 would have been 1/1,000,000th. The log of 1/9 or log of 9, that's going to be probably some decimal. So let's see what that is. Log of 9. That's going to be some type of decimal. So we'll have to round that. And let's round it to 4 decimal places. So 0.9542. So 9542. Does that 2 stay or does it round up? Well, since there's a 4 after it, it will stay as a 2. So 0.9542 would be that. So that means 10 to the 0.9542 should be darn close to 9 if I actually did that math. So, because we did round it, 10 to the 0.9542 would equal right at 9, 8.999. So that's really, really close to 9. So the log of 5.4, I can just type in log 5.4, close my parenthesis, and that gives me 0.7323 or 24. So that fourth place would be 1, 2, 3. That fourth place would be a 3, but since there's a 9 after it, it rounds up to a 4. So that would round to 0.7324 if I was rounding to 4 decimal places. So using a calculator, express these to the nearest 10,000th. So again, that's 4 decimal places. So again, the natural log of 5 is the way that we read this. So this is read as the natural log of 5. And the natural log of 5, what that means is the base of z. So this really means log of 5 base c. But instead of writing like this, they just write it as a shortcut, natural log of 5. That's understood to have a base c. So what this is asking us is e to the what power would give me 5. So if I take the natural log of 5, and if I round that to, notice we don't have to put that second parenthesis in there either. So let me get rid of this here. Natural log of 5 is how that's read. Let's see here. So if we round it to the 10,000th place, that's 4 decimal places. So it's going to be 1.609. Do we keep the 4 or do we round it up? So since there's a 3 after that 4, we just keep the 4. So 1.6094 would be the 10,000th place. So if I have e to the 1.6094, that should be really, really close to 5. Looks like I didn't type it in correctly. Try that again. 1.6094. I'm still not typing it right. 1.0694. That looks correct. So that's how we do get. We didn't get anything close to 5, did we? At 2.9, that's like 3. Interesting. I have to think that for a second. So the natural log of 5. That's only giving me like, wow. So let's do this. I'm interested there. I'm just kind of curious there. That's so far off. So the natural log of, nope. Clear that off. E to the, wow. So rounding it that much changed the answer that much there. So if by just rounding it, it changed the answer drastically. So yeah, rounding does make a big difference there. So if I want to do the natural log of 4.5, that's going to give us 1.504. Now, do we keep the 0 round up? So there's a 7 after the 0, so it's going to round up to a 1. So 1.5041 would be that one. The natural log of 948, natural log of 948. Again, that's going to be the exponent of the e. E to that exponent would give us 948. So if we round that to the 10,000th place, that'd be 6.854. Do we keep the 3 or we round up? Since there's a 5 after it, that 3 has to move up to a 4. So 6.8544 would be rounded to the nearest 10,000th place. Okay. So evaluating some equations here. So if I want to evaluate the log of 256 base 4 is equal to x, notice how we can put this in exponential form. 4 to the x equals 256. So we can also ask ourselves, can I change 256 to a base of 4? So 4 to the x is 4 to some power going to give me 256. Well, if we go 4 times 4, that gives me 16, times 4 is 64, times 4 is 256. That was 1, 2, 3, 4 fours. So if I change 256 to 4 to the 4th, notice that if our bases are the same, then what has to also be true is our exponents have to be equal. So notice how x would have to equal 4 would be the solution to that. So if I have the log of 1/27th equals x, what this means is 3 to some power would equal 1/27th. We'll start with just getting to 27. So if we go 3 times 3, that's 9, times 3, that's 27. So to make it a 1/27th, we'd have to have a negative exponent. So 3 to the x would be the same thing as 3 to the negative 3, because 3 to the negative 3 is 1/27th. So notice how, for this to be true, x would have to equal negative 3. So x would have to equal then this negative 3. So we have that kind of situation going on. We also have what's called the ChangeBased formula. The log of a base b is the same thing as the log of a over the log of b. And also, if these become common logs, which I can use on a calculator, or I can also write the log of a base b as the natural log of a or the natural log of b, those would be equivalent. So we can kind of actually do these a couple ways here. So if I want to work these out using a calculator, log of 343 base 7, I can actually write this as the log of 343 over the log of 7. So I can use the common log, the log of 343 divided by, oops, got to close that parenthesis there, divided by the log of 7. That gives me 3. Notice that you also could done the natural log of 343 over the natural log of 7, because that's also on the calculator. So if I do the natural log of 343 divided by the natural log of 7, that also gives me 3. Now we do have a change base on our calculator as well. If I hit math and go down to A, use that one, I can also type it in that way. So the 7 is the little number, and the 343 is the big number. And that also gives me 3. So there's 3 ways I can actually put that into the calculator. So that would be A. So if I want to do B, I can do the log of 256 over the log of 4. I can just use the common log if I want. Excuse me. So the log of 256 divided by the log of 4, that gives me 4. On C, I could do the log of 8 base 3, the log of 81 base 3. You could use the ln button if you want. Ln of 81 divided by the ln of 3, and that would give you 4. So the natural log of 81 over the natural log of 3 would give us 4. On D, if you want, we can just keep that the same, the log of 28 base 5. And we can also use that special button inside the math area. So math, go down to A, hit that one, and put the little 5 there, and the big value is the 28. Now, again, that really reads as the log of 28 base 5. If I hit enter, if I round that to 4 decimal places, that would be 2.070. Do we keep the 4? Yeah, we would keep the 4 since there's a 1 after it. So 2.0704 will be that answer if I carry it out to the 10,000th place. Lastly, we have some formulas here as well that we involve the logarithm. Logarithms, you'll see them throughout science. You know, if you work with chemicals like acids and bases, there's logarithms there. There's what's called exponential growth and exponential decay. You'll see logarithms there. This is an example involving sound. It also involves a logarithm to solve this application. So the loudness of a sound is measured by a unit called a decibel. A very faint sound called the threshold sound is assigned an intensity of I sub 0. Other sounds have an intensity of I, which is a specified number of times the threshold sound. So I would equal n times I sub 0. So if I multiply some number times I sub 0, that gives me the actual intensity of I. So the decibel rate is given as the formula is going to be 10 times the log of I divided by I sub 0. Find the decibel rating for sounds having the following intensities. So the first one has intensity of 110 I sub 0. That's a whisper. So whisper it's 110 times the threshold sound, which is I sub 0. So the decibel level can be calculated by going 10 times the log of. Now, I is going to be equal to n times 0. So n times up to 0. So I can actually replace I with that. That's going to be over I sub 0. So that's how the I sub 0 is actually divided out of this problem. And so we have this 10 is going to be equal to the log of actually just the 110, because the I sub 0s are actually going to drop out. So if I can do 10 times the log of 110, that's going to give me my decibel level, my sound intensity, if you will. So using my calculator, this is a common log. So I have 10 log of 110, and that gives me then, and again, if we round that to 4 decimal places, that's going to be 20.4139, and that's going to be decibels. That's going to be the sound. So we have that going on. So whisper would be considered about 20 decibel levels. So speaking voice should be much louder. So the decibel level for speaking voice is going to be the 10 times the log of, and what we end up with then is that I sub 0 divides out, and all we end up with is the log of 230. So if I use the formula there, 10 times the log of 230, that'll give me my decibel level of 23. So 23.6173. So a lot of times, these may be probably rounded to the nearest whole number, 20 decibels. This would be probably 23 or 24 decibels if I round it up there. So we'd have that involving logarithms. So who knew logarithms are involved in sound intensity? So, like I say, if you get to studying a lot more in science, you'll discover there's a lot of math in science that's kind of cool. Well, that concludes my little lesson on logarithms.